B. This implies x belongs to A. Here we are using law of simplification, because if you have two statements and their conjunction, then that implies either of the statements. Law of simplification, we are simplifying from two statements to one statement. Always remember that it involves conjunction, not disjunction. Okay, x implies A, hence, now in this case there is no other direction since we don't have equality here. This is a weaker statement than this. So A intersection B is a subset of A. Now if you recall, in the previous similar property involving union, there also we did not prove the other property from scratch. We have used the already proven property along with something else to prove the other one. Here also we are going to follow the same procedure. We already know this, okay? So that means A intersection B, this can be written also as B intersection A. Where is this coming from? It's coming from the fact that intersection of sets is commutative. The first one, what we have proved today. Now, you see, you have this. That means you have the first set. So, this is a subset of B. So, using what you have already proved, you have got this one also. Okay, so that finishes the third part. And the fourth one, if you remember, it was somewhat more complicated than the previous three. The fourth one, what it said, A intersection B is equal to A if and only if A is a subset of B. This will also go along the same lines as the previous one involving unions. Nevertheless, since we are proving everything, we do this one also. So first, now this has two parts. You assume this, prove this, then again you assume this and prove this. First, assume A intersection B is equal to A. Now we have to prove that A is a subset of B. So let X belong to A. Okay? X belongs to A. Then, now since A is A intersection B, so X belongs to A intersection B, which implies X belongs to A and X belongs to B. Okay. Now you see this is again a conjunction, P and Q. Just now we have used law of simplification. This in turn implies, or you can just write this implies X belongs to B. Why? You already know why. To get this from this, we have used the law of simplification. This is P and this is Q. That implies P and Q implies P, or you can write Q also, since that is also allowed. But we don't write the reason. Okay, if the what we are doing is very elementary, or if it is obvious what we have done, we don't write the reason. Always we don't write the reason. Okay, so you just simply write this implies X belongs to B. Okay, we keep on saying law of simplification, but sometimes it is better to not refer to something without understanding. Sometimes without any elaborate law or anything, you just simply think of the situation. X belongs to A and X belongs to B. If I choose to ignore this part of the information, I just simply write X belongs to B because that is also true. So that's what I have done here. If X belongs to A and X belongs to B, then obviously X belongs to B, and this is the part I need. So that means having chosen X in A, I have proved that X is in B. Hence, A is a subset of B. The second part of the proof you write in the second paragraph. Next, assume, okay, one more thing. This sort of statements where we have to write assume, define, suppose, it's better to write we. First, we assume. This seems more polite. Okay, if you are writing a solution in an examination, then the grader or the examiner will also look for this sort of thing. Otherwise, you may lose points or marks. Okay. Next, assume when we go to higher mathematics, this sort of niceties or formalities are minimized. We get rid of words like that and we keep the thing formal and we just write first assume. It is less polite because it is somewhat like ordering someone to assume. But when we are writing for examination, it is smart to be polite for the sake of marks. Next, assume, we have to assume this one. A is a subset of B, and we have to prove this. In the beginning, when you write things, at school level, you write everything, right? For example, in this part, instead of writing this, we first of all first assume this, then we are going to prove that A is a subset of B. That has to be mentioned. Otherwise, marks can be deducted. Okay. Similarly, here also, next assume A is a subset of B. We prove this is equal to this. Okay, you write those things, all the details. I am going to leave them out. So now we have to prove this. So what I was going to write, instead of writing those details, I was going to write we already know what do we know? A intersection B is a subset of A. This was proved in the third property. So one part we already have. For the other one, let Y belong to A. You see, I have taken the variable element, I am writing for Y for that here, since I have already written X here, but you can write X here since it's variable. Okay, that does not matter. You can write X, once something has been done and it's over, then you can again write that same variable name, but in a given proof, in a given part of the proof, if you use the same variable name for two different variables, then you will, that is a mistake. Okay, then you will come across some logical fallacy. But this part is over, so although I have written Y here, I could have written X also. So let Y belong to A. Then y belongs to B as well. Where is this coming from? Because A is a subset of B. Thus, y belongs to A and y belongs to B. Because under this assumption, our steps look like this. This is A, this is B. A is a subset of B. So if y is here, then y is in B also. That's what we have written, which implies y belongs to A intersection B. Now what have we proved? We have taken any element in A, we have proved that that element is in A intersection B. So A is a subset of A intersection B. Combining this containment and this containment, you get this equality, thereby proving the other part of the proof also. And now the proof is over. Okay, now at this point, it may seem to you that these things are somewhat boring. If you have started to understand why the things are true and why the things are behaving the way they are, then they may start to seem somewhat boring. But you see, it's like learning the alphabets in a language. For example, English. That is not the most exciting part. But once you learn the alphabets, then you start to form words. Then you start using those words, you start to form sentences, and then you go writing paragraphs, and then eventually you write a story, which may be extremely enjoyable to read. Same is the thing with mathematics. The beginning parts, if you, how to put this? If you are able to overcome this initial boredom of the elementary things, then you will get to the interesting things. Without the elementary things, if you don't have the alphabet, how can you read a story? So bear with this part. We will come to the more interesting part, and if you have passion for mathematics, then of course you will do anything for it. But if you are using mathematics not for the sake of mathematics but for something else, then also these parts are necessary. Okay, so you just take them as a bitter pill which will help you overcome any element that you are having right now. Okay, so you can view it like that. Now next, after intersection, we came across in the previous video many properties involving difference of sets. So let us recall them one by one, and I think I have proved only one property, one of the De Morgan's laws. So now I am going to prove the rest of them, but to save you from the boredom that you may be having right now, I will go through them in a sketchy manner. Okay, so the first one was this: A minus B is not equal to B minus A if A is not equal to B. Okay. So to prove this, we are given that A is not equal to B. Now A is equal to B means what? If you remember, of course you remember, we have been using it so many times. The principle of extensionality of sets. A is equal to B is equivalent to A being a subset of B and B being a subset of A. Now A is not equal to B means what? This is not the case. I mean, you see that is why mathematical logic is important. What we have here is the negation of this. That means we have this. Negation of A equal to B is A is not equal to B. So that will be equivalent to what? Negation of this. Now, negation of a conjunction is what? P and Q. If you recall from mathematical logic, there also we had De Morgan's laws. This is equivalent to negation of P, negation of Q, but and changes to OR. Okay, so this is equivalent to, if you think of this as P, that means negation of A is a subset of B, or negation of B is a subset of A. Okay, this is the thing we have used here. Now I am writing this in a more simple manner. Negation of A equal to B is A is not equal to B is equivalent to A is not a subset of B or B is not a subset of A. Okay, so from this we have this, and you can see here how we have got this. Okay, so this implies A is not a subset of B or B is not a subset of A or both. Remember, OR means exclusive OR, so it includes the possibility of having the both the things. Okay, so if we have this, right, then you think of the situation in terms of Venn diagram. This is B. A is not a subset of B. Being a subset of B means what? If we had A is a subset of B, if A was the subset of B, then every element of A would be in B. This means there is at least one element in A which is not in B, which is preventing A from being a subset of B. A situation somewhat like this. This is A. There is at least one element in A which lies outside B. Okay. So, if this is the case, so what you do, if you write if this is true, then there exists some element A belonging to A that is not in B, or in other words, A belonging to A minus B. Okay. Or if you find this difficult to understand, A belongs to A such that A does not belong to B. Now, if A has an element which is not in B, then clearly A cannot, that's not what we are proving, sorry, I mistook it for something else. Then A minus B is not equal to B minus A, okay, such that this, hence, since A belongs to A and A does not belong to B, so that means A belongs to A minus B. Okay, A belongs to A minus B. However, A does not belong to B minus A because A does not belong to B. You see, it's like this, no? This is A, this is B. There is at least one element A in A which is not in B. That means it is in A minus B. This part is A minus B. And because it is in A minus B, it cannot be in B minus A. Why? Because this part is B minus A. Since B minus A is a subset of B, if an element does not belong to the bigger set, how can it belong to the smaller set which is inside the bigger set? So that's why we have written A does not belong to B minus A because A does not belong to B. That's the reason. But then we have, but then A minus B cannot be equal to B minus A. How can they be equal if one has an element which is not in the second one? Similarly, if you have to consider this case also because this case is different from this one. If you have this, exactly the opposite thing happens. You have an element in B which is not in A and the rest is similar. In place of A minus B, you will then have B belonging to B minus A. But then B does not belong to A minus B because B does not belong to A, and that will give you the fact that B minus A is not equal to A minus B. So in any case you are having this. If this is the case, then this is true. Now recall one more thing from mathematical logic, namely the contrapositive of a statement and the result that says that a statement, an implication and its contrapositive are equivalent. That is, P implies Q is equivalent to negation of Q implying negation of P. Okay. Now this is an if-then statement, right? That means this is the hypothesis and this is the conclusion. Hypothesis, conclusion. So we can rewrite this like this. Implies A minus B is not equal to B minus A. Instead of this P implies Q, you can write it in this form. That is also the same thing. Negation of, this is P. Okay, this is Q. Negation of Q means what? Q is A minus B not equal to B minus A. Negation is A minus B is equal to B minus A. Negation of Q implies negation of P. P is A is not equal to B. This implies A is equal to B. So this looks like another result which says that if A minus B is equal to B minus A, then A and B have to be equal. But this is nothing but another way of saying the same thing. Okay. Next, what we had, A union A, okay, partition. A union A complement is equal to universal set and A intersection A complement is empty. Okay, now we already have what? A is a subset of U, and or instead of dividing it up into two parts, we can at once write we already have A union A prime is a subset of U. Where is this coming from? This is coming from the definition of universal set. When you write a universal set, it is assumed that any set under discussion is a subset of the universal set. From that, this is coming. Okay. We have to now prove the reverse containment. So we take any element in the universal set. Now this implies X belongs to A or X does not belong to A. You see, actually this has to be written, but what I am thinking is that, you see, this from in this implication, the hypothesis apparently has no relation to the conclusion. It is something about U and this is something about A. Okay, but if you remember, in an implication like this, there need not be a causal relationship between the hypothesis and the conclusion. All we are concerned about here is the truth or falsity of both the statements. Okay, that will determine whether the implication is true or not. So you just have to have statements here. There may not be any relationship or any relationship that is immediately apparent from the situation. So I have written something here, I have written something else here. The question is this implication true? This is of course my assumption, and this is always true. Why? If you recall, see, everything is coming from mathematical logic. Without mathematical logic, you cannot take a single step. Law of exclusive middle. You see, a statement and its negation, if you take their disjunction, that is always true. A statement is, that is because a statement is either true or false. Okay, that is always the case. There cannot be anything else. Either a statement is true or it is not true. Now from here, so because of the law of exclusive middle, this statement is true. Okay, not the implication but this statement alone, the one within this oval, that is true. Okay, now this can be written as, because true statement implies true statement, that is a true implication. That's why this implication is valid. Or now X does not belong to A means what? Since U is a universal set, so just like every set is a subset of U, every element is also an element of U. That means X is an element of U, but X is not an element of A. That means X is in the complement of A. Being in universal set is a truth. That's always the case. X is here. So X is not in A means X is in the complement of A. Okay, so this is the complement of A. But this implies what? X belongs to, since you have OR, this. So you also get this containment. A union A prime. From these two containments you have the equality. Okay, now we prove this one. There is a language for the, there is a term for this situation. If you recall, this is the same as saying that A and its complement are disjoint. When two sets have empty intersection, they are said to be disjoint. So this also will be proved somewhat like the contradiction proof that we carried out previously. We will start by supposing an element in this. So this is a small point that you can remember from these discussions is that if you have to show that some set is empty, you suppose the set has at least one element, then run into a wrong statement, thereby proving the supposition is wrong and hence there can be no element in the set, proving that the set must be empty. And since there is only one empty set, so it must be equal to that empty set. So suppose there exists an element x belonging to A intersection A prime, then x belongs to A and x belongs to A prime, which imply x belongs to A and x does not belong to A. Now an element belonging to a set and at the same time does not belonging to the set, that is an impossibility, it cannot be. But this is not possible. Hence, our supposition is wrong. That is, A intersection A prime cannot have any element. This implies this, that it has to be empty. So this is one thing involving complements. Then there are many actually. The complement of a set is equal to the set. Let me just write some of them. Then A minus the empty set is equal to A. A minus A is equal to the empty set. A minus U is empty. What else? A minus A prime is equal to A. A prime minus A is equal to A prime. Right. Then U prime is empty set. This set prime is U. A minus B is equal to A intersection B prime. Okay. And there is one De Morgan's law that we have not proved. That is this one. A intersection B complement is A complement union B complement. Finally, yeah, if A is a subset of B, then A minus B is empty. This one we prove first of all. So for to prove this one, we start by taking an element x in A. Now if x is in A, then it cannot be in A complement. Why? Because we have already proved that A and A complement are disjoint. So if something is in A, it cannot be in A complement. So x does not belong to A complement. But not being in a set means what? Means it belongs to the complement of the set. So x does not belong to this set. That means x must belong to its complement. Okay? Now conversely, if we come from the other direction, if x belongs to this, just simply using the definition of this outer complement, this implies x does not belong to A complement. But then again, using this, if x does not belong to A complement, then it has to belong to A. Now where is that coming from? If you see, like